Any questions before we start? Good. As usual, I'll remind you where we were. It was a sort of a sharp break yesterday on Tuesday, so it's maybe good to have a reminder. So last time we showed what I call the easy side of the chain rule. We showed that C of xy was smaller or equal to C of x plus C of y given x plus some error term, which I'm going to be, while we were doing the proof, we had some error term that was first of order of log of C of x. Right? Because we had a 2 times length of C of x plus O of 1 at some point. We had that in our derivation. And just to remind you the idea, how did we prove this? We proved that, well, we're looking for a bound on the shortest program, an upper bound, on the length of the shortest program, which prints x and y. And so we came up with one program, as usual, to print x and y, which was involving the shortest program for x star, and the shortest program for y relative to x, that we called q. So this had length C of x star had length C of x, q had length C of y given x by the way we defined the q. And then we had a delimiter problem. We needed a routine which was saying, oh yes, there's x star and q, but you need to break this into two pieces to understand them properly. And so we needed some information about the length of x star. This is why one idea that we had was to give C of x bar in a self-delimiting way, which was explaining the 2 length of C of x plus 1. The plus 1 was absorbed here. So all that to say that I could have, proved this claim instead of the one that I wrote down. But instead what I did is I said, yeah, well, it's smaller or equal, then this doesn't change. But instead I had plus O of some log n. I involved the parameter n, where n was defined as the max between the length of x and the length of y. Okay, C of x is smaller than the length of x, so it's smaller than the max between the length of x and the length of y, so this follows. It's a more conservative bound. And I was very rightly asked, or it was observed, that why am I using this bound here? It's very conservative. I could have just written it this way, or even written the minimum between the two by some different argument. But and here's going to come perhaps the more relevant justification. So that's another proposition now. Chain rule hard side. And here it is. For all strings x and y, so the chain rule will be that this quantity here is equal to that quantity here up to some error term. So the hard side will be obviously it's the other side, which I like to write this way, just on the other side. C of x plus C of y given x is smaller or equal than C of x and y plus some error term. And this, there again, I will do one tight bound and one conservative bound. The tight bound cannot be the same one as the tight bound we had here. The tight bound is order of log of C of xy. Is it clear if I write log of C of xy, you understand that we're taking the log of that number? Technically, perhaps I should be putting an extra set of parentheses, but sometimes it's even more messy when there are too much parentheses. Okay. And so, yeah, like if I really want to be consistent, this is why I had plus O of log n, where n is the same here, is the same n here. Because C of xy is going to be smaller than C of x plus C of y given x. So I could say also smaller than C of y, ignoring x. And so worst case, I'm summing some length of x plus length of y. So it's worst case, I'm summing 2 times n. And this is why this quantity here is basically smaller than 2n, or 2n plus order of log n. So it's smaller than 3n. So it's order of log n. I mean, order of log C of x and y is going to be order of log n. Basically, because as I said, C of xy is smaller than 3n plus some constant. I say 3n, really it's like 2n plus O of log n, but then this is just O of n. I'm all absorbing this into O of n. So C of xy is the same as O of n, and so I can take it like this. Okay, but maybe if you want a tighter bound, then we're happy. We've got that to show. I am not going to show it. But to put something, yeah, maybe I should just insist. Also here, n is the max between length of x and length of y.
The very right top, it should be the length of C of x is less than 2n plus half n, right? Ah, no, no, sorry, yeah, no. Yeah. This is the complexity here, yeah, sorry. Yeah.
In fact, yes, sorry, I was a bit sloppy here, but use this C of x plus C of y given x, and then you can do another smaller or equal, because C of y given x is always smaller and equal to C of y only.
Yeah.
We've seen that last time. So it's C of x plus C of y, plus error terms. The error terms are a bit annoying, but they're negligible. But then this is length of x. It's upper bounded by length of x. This is upper bounded by length of y. So I've got this one plus this one, which is smaller than twice this one. This is where the 2n comes from. And then if you really want to be precise, you have to say, oh, well, then we have log of O of n, but you can verify that it's O of log n. Right. Okay, so let me just state as a theorem, just a concatenation of our two statement, chain rule. Maybe chain rule for plane complexity. It's worth saying it. I usually do this. Right? Again, for all x, for all y. C of xy is equal to C of x plus C of y given x plus, well then I have to choose an error term. One that I cannot choose is this one, because here I really have O of log of C of x and y. But a term that is order log of C of x and y is larger than a term that is order of C of x only. So, to be neat, I can use this one, O of log of C of x and y. Right, and I could have chosen also this one, order of log n. Sometimes it's just more, it's practical to have some parameter which just depends on the length of the strings, x and y. Now here, the error term depends on the complexity of x and y, but technically, this is a tighter bound than the log n. So I'll just write this one for the plane complexity. Note that there is some annoyingness in the fact that we have this error term. It would be cute if we can have a chain rule that holds up to O of 1. Up to O of 1 is the best we can hope for in algorithmic complexity, right? Just the choice of the reference Turing machine leaves the O of 1 ambiguity. So it would be neat if I can write something like complexity of x and y equals to complexity of x plus complexity of y given x plus O of 1. As I say, as all equations in algorithmic complexity typically hold up to an O of 1 term. We'll come back to that. For now, are there any questions? Okay. I don't yet know what I'm going to do with the proof of this. I just don't know. It would be long to do it in class, and it would not be the most powerful result. So one of the reasons why I'm not doing the proof is that we're going to wait for prefix complexity. We're going to have a stronger notion of a chain rule. So might as well not spend an hour on that proof. Problems? It would be an annoying question, both for you and for me. I don't exactly know how to help you build the solution. So I don't know what to do with this proof. But that's just my problem. At least I'm honest with you. I just don't know yet if we're going to see it, in which case and how, but we'll see. I have to decide.
On the easy side, we had the intuition that like you can compute x and then give x as side information. But so on this side, there is no kind of intuitive...
I would love to tell you an intuition, but no. And to tell you the intuition, I would have to re-dive into the proof, re-understand it properly, and it's a matter of recursively enumerating 3 sets. It's very beautiful. I read it again this morning. Funnily, it's in a part of my thesis. I sort of have to use the proof in a part of my thesis. And I was reading the textbook, and I was like, oh... I remember when I was preparing my PhD, I had to really understand the proof that was in the textbook. But sometimes when it's somebody else's proof, your brain doesn't really process it the same way. So instead I reread the part of my thesis. I was like, oh yeah, okay, I got it again. But all this effort for me reading it this morning to decide I'm not going to do it today. Because it would probably take the rest of the seance of the course to do it properly. So let me move on. And when we're going to go to prefix complexity, we're going to have, this side, I'm spoiling myself, with O of 1. And we're going to have a proof of it. But it's completely different. So there's still value into understanding this proof for plane complexity. But I have to choose what I talk about in this course and what I don't talk about in this course. Okay. So what I have chosen to talk about next, incompressibility. Maybe another section if you want. Incompressibility. Sorry, unless there was any questions. Any more questions? Good? Okay. Right. It's easy to come up with compressible strings. I told you pi, or the 10 to the 10 first digits of pi. We can find programs that are much shorter than 10 to the 10 bits, and that compute the first 10 to the 10 bits of pi. Or I'm going to do something even more striking here. Let me just say what I said. Write what I said. It is easy to come up with highly compressible string. For instance, define some function which grows very, very, very fast. I'm going to choose one of them, a tower of exponential f of k as, so it's 2 to the 2 to the 2 to the 2, and I've got k 2's. Right, and to give a precise meaning to that, you have to start here. So it's 2 to the 2, that's 4. And then it's 4 to the 2. No, sorry, 2 to the 4, that's going to be 16. And then 2 to the 16, that's a number I already cannot name. And then 2 to that number, and k times. It's just one way to define a fastly growing function. So k times. I'm sure you can come up with more creative ways of defining functions that grow fast to infinity. Now, observe that for each k, so maybe fix one k if you want, or the string f of k. Okay, yes, what's f of k? F of k is a number. I've defined it as a number, but yeah, each number can be mapped into a string. It's going to be a long string to write it down. The string f of k does not have a large complexity. In fact, the string f of k has complexity at most c of k, c of k plus little c I'm erasing just to write it down here. And C of k plus little c, which is smaller or equal to log of k plus little c prime for c or c prime independent of k. They're independent constants, where c and c primes are constants. Independent of k. So why? I'm claiming that this string here, right, if you want, take k to be 1000, just so we can set our ideas. I have 1002s that are stacked into an exponential like that. It gives me a huge string, right? The length of the string is basically the log of f of k, but the log is irrelevant in front of the tower of 1002s. So it's a very long string, yet it has complexity at most log k plus a little constant. Why? Because, well, think of it. There's a short program for f of k. You can just program this recursively if you want, exponential 2 to the power of, and you have to input k into your program. So in my example, I said 1000. It seems like 1000 is like an irrelevant parameter, but if I keep it general, if k is a general parameter, then to compute f of k, I also need to hard code k into my program. So this will be the c of k bits. I'm giving a program for k plus a constant, which is, this constant embeds the program f for the function f. And k embeds, the complexity in the parameter k. But what matters is that it's quite small, the complexity. It's log of k, whereas the length of the string is huge. So c and c prime, I'm sort of stuck because, c of k is smaller than log of k up to a constant. So maybe I need to add a different constant c prime. This is just to take into account my O of 1s. But yeah, I guess the punch is yet f of k as a string has a huge length. Okay, so it's just a fun way to come up with highly compressible strings. By compressible, I have not formally defined it, but I mean it's a string whose complexity is much, much, much smaller than the length of the string. So this string f of k has a huge length, yet it has a small complexity compared to its length. I'm not claiming that this way of the program that I can exhibit for f of k is the shortest one. But again, it's one program, which is much shorter than its length. So the complexity of f of k is smaller than what I have found. And so it's small. But what about incompressible strings? So it's easy to come up with compressible strings. What about incompressible strings? Is it easy to come up with them? Do they even exist?
Something like total random symbols.
What does that mean? Total?
Yeah, because I was thinking, strange to explain. If I have, for example, something that be computable by a Turing machine, by a function, is able to describe. But if I guess something that is not, and the only thing that I have in mind that is not is something totally random, the minimum length of the description is the string itself, I think.
Yeah, your intuition is right. You're spot on. That will be the idea of what we had as an incompressible string. I'm going to give a formal definition of what we mean by incompressible, and it connects to what I have named algorithmically random. You know, in my motivation for the algorithmic complexity, I think 4 or 3 lectures ago, I spoke of, oh yeah, when there's patternless, as Matteo said, when it looks like a bunch of nothingness, there's no patterns. Well, the idea is that probably that the shortest program for that string will be, quote, the string. If that really is the shortest program for that string, we will say it's incompressible. Its complexity is as large as the length. In contrast with what we've just done here, we've exhibited a string whose complexity is much smaller than its length. So, correct. But maybe as a first, just thinking about what algorithmic complexity is, it seems awkward to say, yeah, that string is incompressible. Namely, its shortest program is as long as the string. Who would I be to claim that? Have I tested all shorter programs? And you realize right away that we might run into very hard problems. Because for me to say, yep, I checked all smaller programs, and they all compute different things than the string x. And the shortest program which computes x is this one. At least intuitively, we feel like I'm running into the halting problem. Because I'm sort of claiming, yeah, I've checked them all programs shorter than this length, the length of the string x, they all give different output. Oh yeah, and those who have not yet given an output, they will just never halt. We already smell something fishy here. So to testify that a string is incompressible is going to be hard, as in perhaps uncomputable in general. We'll come back to that. But maybe first, it would be somewhat satisfying to say that at least we can prove that there exist incompressible strings. Without being able to say, oh yeah, this one that I have come up with is incompressible, that's a different task. But at least to say, mathematically speaking, there exists at least one string of length n whose shortest program is greater than n. And that's what we're going to do. So now I was sort of intuitive with my notion of compressible and incompressible. Let me be slightly more formal here. Definition. And for each C, a string is C incompressible C is a number if I'm going to leave some space. Well, how would you naturally come up with a definition which relates, I'm going to give you a hint, obviously C of x. We want the complexity to be, oh, sorry, I think it might be a bit confusing, but the smaller is C, the more incompressible it is. So we want the complexity C to be larger than larger or equal to the length of x, right? And we might give a little loose of C bits, minus C. So it is 0 incompressible if its complexity is larger or equal to its length. It's 1 incompressible if its complexity is larger or equal to its length minus 1 bit. Right? We just have a parameter here. Okay.
But also, for example, epsilon or one character string are incompressible.
Well, yeah. It's a little annoying when they're very small. But when you look at epsilon in this definition, it's hard for its shortest program to be shorter than the length of epsilon. The length of epsilon is 0. So, what's the shortest program for epsilon? Well, obviously, it highly depends on your programming language, and this is where we run into the ambiguity of the constant. But if you fix one programming language, or if you fix an enumeration of Turing machines, and we think of Turing machines, it might be the case that the shortest program for epsilon has length 55. I don't know, because all other strings smaller than 55, they give nonsense, or they give other, I don't know, it might be 17, I don't know, but it will be larger than 0. So yeah, epsilon would qualify as a incompressible string. It obviously becomes interesting when we look at n-bit strings, strings of a length n, for some parameter n, and we see that c is a constant independent on n, and then we're going to go like, oh, yeah, that's an incompressible string.
C is supposed to be non-negative, right?
Yeah, c is a positive number. Good point. Okay. Proposition. There are at least some number which is 2 to the n minus 2 to the n minus c plus 1 strings of length n that are C incompressible. Okay, so the number is 2 to the n minus 2 to the n minus c plus 1. So there is a certain number of strings that are C incompressible for each n. Maybe put C equal to 0, which is the strongest form of incompressibility that we have here. You know, a string is 0 incompressible if its algorithmic complexity is larger than its length, larger or equal than its length. What happens if I put c equals to 0? Well, I've got what I want. I've got 2 to the n minus 2 to the n plus 1. So I have at least one string which is 0 incompressible. That is incompressible. And let's prove that. Well, first thing to mention, the number of strings of length n is, how many strings of length n do we have? 2 to the power of n, correct. We've got 2 to the n bit strings. 2 choice for each bit. And fine. The number of programs of length strictly less than n minus c is, why am I looking at programs of length strictly less than n minus c? Because I'm looking for c incompressible strings. So for strings for which, well, for strings that cannot be computed by a program of length strictly less than n minus c. You know, if a string has a program of length strictly has a program of length strictly less than n minus c, it would not be c incompressible. It would be c compressible, if you want. So what's the number of that programs, those many programs? Well, I've got programs of length 0s, I've got 1 of them. Programs of length 1, I have 2 of them. Programs of length 2, I have 4 of them. Programs of length 8, I have 3, I have 8 of them. So what's this sum? Well, I have to sum over I equals 0 to strictly less than n minus c. So my upper bound is n minus c minus 1. So I here refers to the length. And I've got 2 to the I programs of length I. Programs are just strings after all. So I'm upper bounding the number of programs of length strictly less than n minus c by the sum of all possible strings of length less than n minus c. Right? And in this sum, so I'm basically summing, here's the program epsilon, which contributes for I equals 0. I have 1 program of length epsilon. I have 2 program of length 1. That's the second term, would be 2, when I equals to 1. And then I've got 0, 0, 0, 1, 1, 0, 1, 1. I've got 4 programs of length 2, that would be when I equals to 2, and so on, until I equals n minus c minus 1. You might recognize the geometric series, or sum. So this is just 2 to this term plus 1, so n minus c, and then minus 1. And the denominator is 1 in this case. right? That's a geometric series. Sorry, do you call it a geometric series? Power series? And now we're going to look at the most conservative scenario. In the most conservative scenario, each of those short programs computes a different string of length n. That's really a conservative assumption. So I'm calling those the short programs, those programs that have length strictly less than n minus c. We've counted them, there's that many number of them. Worst case, all of these programs happen to halt and happen to be computing a string of length exactly n and not the same, always a different one. There's good reasons to think that that's not the case. Like we're going to have like some of those short programs in fact never halt. Some of those short programs compute epsilon, obviously. So not a string of length n. There will be a pair of those programs, or 3 or 4 or many of those programs which compute the same string of length n. But here we're making a very conservative assumption that they all compute a different string of length n. Therefore, the number of strings that are not computed, the number of strings of length n that are not computed by such a program is going to be larger or equal to, well, this number here minus this number here. Thus, there are at least 2 to the n minus 2 to the n minus c plus 1, this number here minus this number here, strings of length n that are not computed by a short program. Less than n minus c bits. That's what I mean by a short program in this case. They are C incompressible by definition. Question? It's basically a counting argument. There's too many n-bit strings for short programs, so they must be strings that are not computed by a short program. Okay, just before the break, I'd like to wrap this up, and in fact, I would be pushing it. Let's have a break and reconvene at past. Okay, so what did we do? Sort of plenty of writing. We want to do it right, so it's fine, but we just saw that basically There needs to be incompressible strings because there is not enough short programs. So they exist. Now, this was our definition of C incompressible. It is, so a string of length n is going to be C incompressible if its complexity is larger than n minus C. Basically, it's length minus a few bits. And we've shown that this is the number of C incompressible string. Can you change color? Okay, let's read this number. What does that mean? So I'm just going to call it a corollary. Corollary. And what about zero incompressible strings? I've said it already. There is at least one zero incompressible string.
Can we do better? Can we find more?
We will. I have to stop making promises. Because every time I say, yeah, we will do that, and I'm like, yeah, the semester is advancing fast. And as you know, I'm building this course as we go, and my big dreams of doing the whole Lee and Vitani 900 pages is sort of collapsing slowly. But it's a nice problem for me because the task is how can I make the most out of the hours we have together. So it's like I have to choose my battles. But I hope we can come back to that. But yeah, because as you see, we did a lot of conservative assumptions, right? Like it's like, oh, we're supposing that all programs shorter than n minus c, they're all halt. They all compute a string of length n. What are the odds of that being true? Come on, like some of them are going to compute other strings of other lengths, and all different strings. So yeah, there are ways to improve these bounds. There is at least one zero incompressible string. That's the first part of the corollary. And it seems a little boring, right? Oh, there's one. Proof of principle, there's one. But what I'd like to stress is that it really goes fast. Okay? Put C equals 2. And you realize that I'll need a bit of space. I guess I have to start erasing my former proof. But if C equals 2, we have 2 to the n, right, 2 to the n, I'm factoring 2 to the n, and then I have 1 minus 1 over 2c, and plus 1. Okay, this is the same thing that I have written here in blue. So 2 to the n, 1 minus 2 to... So when c equals 2, it's 1 minus 4. It's 3/4 of 2 to the n plus 1. So the plus 1 enables me to write more than 3/4 of the strings are too incompressible. Okay, so there's a lot of strings that are basically incompressible. There's a remark I'd like to make just before wrapping this section up. what is it? Yeah, in the proposition and even in the definition of compressible strings, I left some space just to realize that nothing changes if we give auxiliary information. So we can speak of, and then I will maybe complete some stuff in blue. For each C, a string is C incompressible given Y if, well, that would become C of X given Y is smaller or equal to length of X minus C. That's just a definition. There's nothing to prove here, but I can speak of C incompressibility given Y. And in the proposition, well, it would be there is at least this number of strings that are C incompressible given Y. Nothing changes in the statement. And why? Because nothing changes in the proof either. The number of strings that have length n is still 2 to the n. And then what's the number of programs that can that exist? It's still the same number of programs, of short programs. It's just that now we have to think of those programs as, they possibly have access to Y. That doesn't change that there's only so many few short programs. Remark? The above also holds with auxiliary information Y. And then maybe C what's in blue. But not this bit. That has nothing to do, but I basically completed here given Y, well then that's the criteria for being, by definition, C incompressible given Y if C of X given Y is larger than the length of X minus C. And yeah, as I said, there's just not enough short programs that even if they have access to Y, there's still not enough short programs. And I shall just mention in closing the section on incompressibility that in my motivation I have spoken of random strings, algorithmically random strings. And for our purposes, we can identify algorithmically random strings with incompressible strings. They have no short programs. This is what we take to be a algorithmically random string, at least in a first approximation of the notion of randomness. Like if you zoom in on some papers, some authors are going to debate that is precisely what should be grasped as algorithmic randomness. Yeah, for this course, let's identify those. Okay, are there any questions about incompressibility?
Yeah, one, well to explain as usual, but I was thinking that in general, if I give you a number, only one number, a digit, it's difficult to say, is it random? Maybe this thing is, there is a join between that fact that low-length strings are incompressible. Because I think that the notion of randomness appears when you have a big set, because it makes no sense, one is random, can be, cannot be, so.
You're right. Yeah.
Yeah, because also
Start. You mentioned epsilon.
Yeah.
But what about the string 0?
Yeah.
Is it incompressible? Well, most likely yes. Again, for the same reason.
Yeah.
Most likely the shortest program for the string 0 is larger than 1 bit, so it fulfills this definition. So yes, this definition acquires meaning for long enough string.
Okay.
In fact, you can define it all the time. It's just that epsilon and the string 0 and the string 1 would qualify as algorithmically C incompressible, but you can also put a little, when you have a publicity and there's always a little star and they say C terms and conditions. In the terms and condition, it should be mentioned, yeah, I've exhibited a 1-bit random string. And then you should go, oh yeah, that's boring. What I'm after is a, million-bit random string. Or the parameter of the length of the string that is qualified to be random, without necessarily specifying what it is, it should matter. Because then you can compare with these constants. Other questions? Okay, my idea was to present plane complexity because it was the natural continuation of our work on Turing machines. I had to just take what we had as Turing machines and define, the length of the shortest program on the universal Turing machine that we also have met in the computability theory part of this course. I want to get as fast as we can towards the other notion of complexity, which we saw as the name is prefix complexity. But I still wanted to give a bit of an idea of, what algorithmic complexity is about. And to motivate further prefix complexity, I'm going to speak about some of the problems with plane complexity. We already met one of those problems, that we found a chain rule. Well, we only showed one side, but I claim the other side holds. But in both sides, it holds up to a additive logarithmic term in the length of the strings, or some other additive logarithmic term in the complexity of the pair of the strings. I'm going to present some other problems, and as we view the problems, we're going to have a larger motivation to introduce prefix complexity. That's the program for the rest of today. Problems with plane complexity. Historically speaking, these problems have haunted the community for 10 years, between the mid-60s and the mid-70s. I sort of displayed a brief overview that plane complexity was discovered first in the mid-60s, and then those problems have been addressed to eventually culminate with the notion of prefix complexity, which solves the problem. One of them, the chain rule holds only up to O of log of C of X and Y. It would be elegant to have a tight chain rule. Maybe that's just a fantasy. Maybe just sometimes we want things to be elegant, but they are not. And it could have been, well, there's nothing to do. The chain rule has to hold up to this. I don't actually. It would be a hard statement because I would be claiming that for any measure of complexity that one would come up with, there's no way to have it tight. I guess what I want to say is maybe we would still be looking for this elegant notion and that we have not yet found it. Second idea, yeah. Okay. Let n be an incompressible number. Yeah, of course, it's encoded as a string, but think of it as a number of length m. Okay, we know there exists. Now consider this string here. 0, 0, 0, 0, 0 for n bits. Okay, which I'm just gonna call short-handed 0n. Yeah, I've got n times the bit 0. It's just zeros. We want to say that it's a very ordered string, that there's no complexity in that string. It's just zeros. But it has length. So it carries with it the information about its length implicitly. Whether it wants it or not, well, has no desires, it's just a string, but it carries with it its length. So the complexity of 0 to the n, we can show that it's equal to the complexity of n, up to a constant, as usual. Which, since I have taken n to be a number that is incompressible, and a number that is of length m, that means it's equal to n plus order of 1. Okay, this last equality just holds from the fact that, yeah, the number n has length m, and I've declared it to be, I've chosen it to be incompressible. But let me go back again to the first equation. How do we show an equation like that? Well, as usual, if you have a program that can print 0 n times, you can transform it into a program that can print n, with just a constant overhead that is independent of n. And if you have a program that can print n, you can transform it into a program that can compute 0 n times, with just a constant overhead and some routines. That's me being fast on this proof, but maybe you can, again, make it formal for yourself. We're going to start to take those arguments as granted. If you want me to give an even more intuitive and even more informal notion, that's just n in unary, that's n in binary. They contain the same algorithmic information. Okay. So we would have liked to say, yeah, this string is very trivial. It's only zeros, but it contains algorithmic information in its length, even if the string is highly structured. That's just one comment I want to make. I'm not going to write it all down. I'm just giving problems for plain complexity. Now consider for the same n, a string x of length n. Okay, one way to write that x is a string of length n is this. X is an element of 0, 1 to the n. It's an n-bit string. And moreover, incompressible given n. i.e., what does incompressible given n means? I want it to be such that c of x given n is larger or equal to its length, the length of x, n. In the last remark, we've seen that we can speak of a string being incompressible given some resource, or auxiliary information I mentioned. Here the auxiliary information is the length of the string x. There is not enough short programs, so these strings must exist. There must be at least one string of length n, whose complexity, even relative to its length, is larger or equal to n. And again being the length of the string x. Now, the fact that I demand that not only that c of x is larger than n, but only that c of x given n is larger than n, it means that, okay, x is a random string. Think of it patternless, plenty of zeros and ones. But the patterns within the zeros and ones in x have nothing to do with the length of the string. It's like if n and x, the bits within x, are different sources of algorithmic information, right? We've seen that a string can carry as a source of algorithmic information its length. And now we're taking a random string, so we'd like to say that in the random string there's two sources of algorithmic information. There's the length, which is, it needs to carry it, but there's also the patternlessness within the bits of x. And so intuitively, that's again a desire, intuitively, we would like that c of x is equal to n, the length of the string x. This is all the algorithmic information within the bits of x, plus n, which is the length of n, because x also carries with it its length. So it also carries the parameter n with it. So it has also n bits of algorithmic randomness, plus O of 1, or O of small term. I'll just write O of 1. And yeah, n would be, so maybe m first. This m should be understood as the algorithmic information carried by the size or the length of x, in the same way that the most boring string was carrying that algorithmic information with it. Its complexity was n, even if it was super boring. And that the other part, the n bits, which is a larger term than m, but still, this would be the algorithmic information carried by the bits within x. Okay, it's like a bit of a metaphoric way of saying that, oh, since x is not going to be highly structured like this string, but it's going to contain plenty of zeros and ones, quotienting out the size, what remains is still, it seems to be n bit of algorithmic randomness, algorithmic information. So intuitively we would like that. And I remind you that m is basically order of log n. This is like basically log n. Because m is the size of the string n. So we might be happy with a measure of complexity which is of the form, if x has of length n, when it's completely random, not only it but also its length, it should be n bit of complexity plus a log n bit of complexity, because its length is also carrying algorithmic information, a quantity of which resembles log n. That's really just my very intuitive presentation. There's nothing super formal here, right? I'm writing stuff like carried by the bits within x, but I hope I can convey an idea. But we have shown that C of x is smaller or equal to n plus O of 1 because of the print x program. This was shown last time. Actually, we showed that it was length of x, but by definition, length of x is n here. Yeah, the print x program is like an upper bound, and the program has size only n bits, so the complexity measure does not exceed n. Okay, again, maybe point number 2 is some ideas that, oh yeah, it's not a bad idea. It has algorithmic information within the bits, algorithmic information in the length. You know, something like maximal complexity could be n plus log n. But, oh well, we've shown that prefix complexity is bounded by n. Too bad.
Plain complexity.
Huh? Sorry, plain complexity, no. Prefix complexity will look like that. A third point that I want to mention, and really the third point I think was the central one. I'm not an expert on the literature and the history of the ideas. I'm actually more attracted by the ideas themselves, but I know that Solomonoff came up with his paper in '64, so even before Kolmogorov. And Solomonoff's idea was very original. It was a brilliant idea. So let me write it down. Solomonoff had a brilliant idea. For a measure over all strings. I write it down and I help you digest it after. The string x is mapped to, I'm going to call it P of x, defined this way. Sum over all programs such that U of P equals x. So Solomonoff was not only interested in the shortest program. He was interested in all programs that generate x. And then what did he wanted to sum? He wanted to sum the probabilities that a monkey would randomly type that program on a computer. Suppose the computer has only bits, zeros and 1. A 5-bit program has a chance, 2 to the minus 5, of being randomly typed by a monkey. So a program P of length of P has a chance 2 to the minus length of P of being randomly typed by a monkey. 2 to the minus length of that program.
So the monkey cannot delete characters.
Cannot what?
Delete characters. It can only read forward. It cannot delete a letter.
Oh, well,
Because I think no, because if it's 2 to the power of minus p is not possible. But I'm not sure.
no, yeah, we take our alphabet of symbols to be binary. You know, sometimes I'm gonna write pseudocode as print x.
Yeah.
But like, if our computer really works with bits, and they do, like whenever we write a key, it's in fact coded into a sequence of bits, but the monkey only has access to those bits. He only can print bits. So I'm going to elaborate more on the monkey metaphor. Yeah, I remember I had my mind like I found it beautiful when I first did like probability courses, and then you find things that well, you know, a beautiful Shakespeare piece is encoded into, well, it's written in English, so in characters, but we all know that we can code that into bits. So by chance, a monkey in front of a typewriter who has access to only a 0 and a 1 might, you know, type some zeros and some ones, and it might happen to be the ASCII encoding of Shakespeare. And this would be, you know, 2 to the minus the length of the string. So that's a monkey in front of a typewriter.
Also, I remember the argument is like a monkey with infinite time. It will eventually write out Shakespeare.
Yes, me too. This is where I found it beautiful. Yeah. So if you take with Borel, Cantelli, Lemma, or can't remember them exactly. Maybe I'm making this name up, but that's what comes to mind. That if you had infinite trials of a non-zero probability event, then with probability 1 it will happen, and it will happen infinitely many times. So, so the monkey in front of a typewriter, you go like, yeah, he might write Shakespeare. Solomonoff idea was like, well, you know what? Put the monkey instead in front of a computer, a universal computer, and that might be more interesting. Because, well, okay, I mentioned Shakespeare, but let me just boil down to again an example that we've met. The 10 to the 10 first bits of pi. You know, I've mentioned many times that there's a short program for pi, so there's a relatively short program for this string, the 10 to the 10 first bit program, bits of pi. If I put the monkey in front of a typewriter, the chance that he types this string is very low. He's gonna have to hit each single good bit of pi. But if I put it in front of a universal computer, he has much more chances of getting it right. Because there's plenty of short programs, including the shortest one, but many others, that will happen by chance to be a program for the 10 to the 10 first digits of pi. Right? And we will be summing, so think of in my example x, the first 10 to the 10 bits of pi. We will, you know, Solomonoff's idea was to sum over all possible ways in which the monkey can write a valid program for pi. So u of p equals x, the chance that he types this program. Okay, and writing this down, this measure amounts to the probability that the program for which the bits are picked at random would yield the string x. By yield, I mean would compute, would be a program that computes the string x. So, okay. Solomonoff's problem was that the measure does not converge. By which, in fact, I mean P of x equals infinity for all x. It's a really serious problem. So for any x that we pick, this beautiful idea, which apparently seems to make sense, like the monkey needs to have some finite probability of typing a program which would yield a computation for x. But as we've defined things so far, and I'm going to explain why, for each x, this sum diverges. Okay. Indeed, there exists a TI, a Turing machine, with some number I in the enumeration of Turing machines, such that on all strings y, Ti of y equals x. So this is for each x. You can come up with a Turing machine who has x embedded into it. Okay, and its rules, it ignores its input. It is going to have large rules. The complexity of the rules of the Turing machine will be as large as the complexity of x, if you want. But it's going to ignore its input y, and it's going to just print x. Okay, so it's like a large and complex I, but that doesn't mind. For each x, there exists a Turing machine which ignores its input and prints x. So, for all its input, it yields into a halting computation, and it prints x. Thus, to translate this for the universal Turing machine, each I bar y is a valid program for x. By which I mean, or as, u of I bar y, which is our encoding for the input of the universal Turing machine. The universal Turing machine on input I bar y, that's the encoding of I and y. It simulates the Turing machine number I on input y. So that does x. each r by y, I bar y, is a valid program for x for all y. In 0, 1 star. Okay, so what the universal Turing machine now does, it has an instruction which is to simulate Turing machine number I on input y, but he doesn't care about the input y, in fact, because Turing machine number I always produces x. But this is a way to generate a family of program. It's just for me to show you that this sum blows up. So I'm generating a family of program which all are valid programs for x. So now let's look at what it does for this sum. P of x is the sum over all programs that compute x. But I'm going to ignore almost all of them, and I'm just going to focus on those. So I am lower bounding P of x, right? Because I'm going to sum over only those programs. And those programs are labeled by y. So it's the sum over all y in 0, 1 star of 2 to the minus length of I bar y, the length of the program. Okay, just to repeat, I've exhibited a family of programs labeled by y for all y in bit strings that generate x. Now, the definition of P of x is the sum over all programs for x. And I'm going to only constrain my attention to summing over this family of programs. So this is why P of x is going to be larger in general. And now let's manipulate this. I'm first going to have the 2 to the minus length of I bar can factor out because it's, okay, yeah. The length of I bar y is the length of I bar plus the length of y. We concatenate bit strings. The length of the concatenation is the sum of the lengths. So I've got that, sum over all y, and 0, 1 star of 2 to the minus y, length of y. Now I think in problem sheet number 1, you've met once a sum of this kind. We have to sum over all bit strings of the length of the bit strings. It's a bit annoying because when you look at the length of the y's, when you order all bit strings, you have a 0 bit string, a bit string of length 0, then you have 2 bit strings of length 1, 4 bit strings of length 2, and so on. So it's convenient to break this sum into 2 pieces. And I'm still going to have 2 to the minus length of I bar as a factor. And then I'm breaking the sum into 2 pieces. First, n equals 0 to infinity. This will be the lengths of the strings y. And then the sum over all y's on 0, 1 to the n. So I'm summing over all possible length. And then I'm summing over all strings of that length. And what I sum doesn't change, except perhaps that now that I have exhibited that each string y has length n, I can say 2 to the minus n instead here. Now this is a sum in y. The sum into y, and it doesn't depend on the argument. So I'm summing something for as many times as there are n-bit strings. I'm leaving n here. If you want, I could have factored this 2 to the minus n here because nothing depends on y in here. and I would sum the empty sum 2 to the n times. So I've got 2 to the minus n times 2 to the n. So I'm summing 1 infinitely many times, and that diverges. It's very annoying because the idea is beautiful. And intuitively, it should make sense to put a monkey in front of a computer and to claim that his probability, obviously assuming a distribution on 1/2 on each bit, is a finite number. So there must be something wrong with the way we capture program size with our definition so far. I think point number 3 is a very serious problem, especially since if we want to develop Solomonoff theory. I'm going to finish here, almost on time today. By the way, I am sorry and I /thank you for letting me overflow, but be free to leave whenever you want, even if that's like in the middle of the class. I never take it personal. And today I'm somewhat finishing on time. Any questions?
I think I sort of disagree with point number 2 a little bit on the second part.
Yes.
Because it seems like when you tell n, m is implicitly known. So for example, like if I was telling you that, okay, there are 5,006,700 and something zeros, like I agree that like the complexity is there in m in that case, for the zeros case. But now if I had a random string, now I'm telling you, okay, so the first one is 1, then there's a 0, then there's a 1, then there's a 2, or whatever, so on. So I don't really have to tell you m, like I'm telling you the n-bit string.
One after the other.
Yes, so why is it n plus m?
Yeah, well, I mean, you are remaking this argument in
Yes,
some sense.
yes.
So you are holding something very solid, like you're like, no, that's a legitimate argument. We've proved it. I cannot tell it to you now right away. I think I'm just going to have to elaborate too much on prefix complexity, which is a topic of next course. But yeah, we will discuss exactly what you're talking about again, because we're going to revisit all of those. As I have promised and claimed that the chain rule is going to be tight up to O of 1 with prefix complexity. Now, spoiling myself, we will realize that it is indeed n plus log n with prefix complexity. So you will see where the argument fails and in what you claim that this will have to fail somewhere, right? Because it cannot both be true. And it will also happen to solve Solomonoff's problem. Do you have an idea, by the way, with the name I've claimed? I said it's called prefix complexity. You have an idea on how to solve all of those? Well, it's clear, it's really not clear how you solve the chain rule, and it's not super clear how you get that, but maybe this. Oh, think about it. We have 5 days before next class. And no, I think for me, it was an important part of the course to express what the problems are. I could have come up with, this is the modern definition, go ahead, and then why you use this as a definition. And I think that by making you live what the problems were, you sort of understand more the motivation of the theory. And Any other questions? Have a nice weekend.